Hello and good afternoon, friends. Welcome to the CEC-UGC live lecture. Dear friends, catering to your needs by conducting numerous sessions and numerous lectures on various subjects, we are here again for you. Dear friends, you might have heard about the term nuclear magnetic resonance. Many of you might be aware with this term and many of you might not be. Some of you might be thinking that it has some connection with creating nuclear bombs. Not at all, friends. Nuclear magnetic resonance, it is an I would say application based sciences which would further result in certain innovations, definitely I would say. So dear friends, as I have already announced that we would be discussing on nuclear magnetic resonance. First of all, we would be studying about its history, and later on we would be discussing on its application. In the later stages within this lecture itself, we would be studying on the concepts, and in our future sessions we would be discussing how these concepts would enable us in studying various techniques. And for this very discussion, we have again with us in our studios Dr. Unnati Gulati. Dr. Unnati Gulati is academic coordinator with Consortium for Educational Communication, that is CEC. So without wasting any time, I would like to welcome our guest Dr. Unnati Gulati, under whose able guidance we would studying the topic nuclear magnetic resonance. Hello ma'am, welcome to the EDISET lecture.
Thank you, Kritika. Dear students, welcome. Today we are going to talk about nuclear magnetic resonance spectroscopy. So this lecture is divided into two parts. In the first session, we will be talking about its applications, and you will be surprised to know that nuclear magnetic resonance is not only relevant for scientists in chemistry, biology, but also in the field of geography. So we will take up those applications, and then we will look at how the history of development of nuclear magnetic resonance in the form that we see now has occurred. Also, in the later we'll take a pause, and then we'll start discussing small little topics like Larmor frequency, like understanding the nuclear spin, and we'll take those topics and try and see and simplify them. And later on we will take them up and we will do all the mathematical and derivations for the respective topics. So let me start with first talking about what is nuclear magnetic resonance and what can it do for you. Why would you like to learn this technique, and in what sciences will it be beneficial for you? So nuclear magnetic resonance can be used for high resolution NMR spectroscopy. Needless to say that high resolution NMR spectroscopy has increased our understanding of all biomolecular processes to the extent that we can clearly understand each and every process atom by atom and can intervene by either means of drugs and molecules or intervene in the terms of enzymes and enzyme kinetics. We can use this technique to study small molecules. We can to determine their structure, their interaction, to determine the covalent structure, as we very much need to do when we do organic synthesis. We need to find what is the product that we have got and what is its chemical structure. So many a times we might encounter isomers, and how do we understand the structure of isomers? So NMR is there to help you there. We have to find cis-trans isomerism, we have to find enantiomers, so there NMR can be useful. These days even NMR is used for studying nanomaterials. All the material sciences, we have polymers, we have glasses, and I would like to tell you that even when we have large chunks of ore of diamonds, one can use NMR microscopy, which is an advanced technique, to find what is in what patches will you find the high quality diamonds without destructing the ore of diamond. So we also have solid state NMR spectroscopy. This has more relevance when you talk about in field of chemistry, in field of new materials. Also solid state chemistry, solid state NMR spectroscopy is also relevant when we do magic angles spinning. We will come to those things little later, but this can tell you about oriented systems, this can tell you about solids. So insoluble compounds which you cannot get into solution, synthetic polymers, which are everyday we create synthetic polymers for everyday increasing needs, and we have very large compounds, so we have to label them and study their composition and their conformations. So we have to determine the structure of the solid state if we are doing the liquid state, and determine the dynamics of the solid state. Another interesting aspect of using NMR spectroscopy is when we are studying food technology. In food technology, every day we are trying to find new methods of food preparation. So when we do these new methods of food preparation, we have to see what is the change in the composition and how the components of the food change as we proceed with the processing. We have wine aging. We can use NMR spectroscopy to check the levels of metabolites or the secondary products that are formed when you keep the wine for aging in the barrels. We can use it to study fruits, fruit aging and fruit ripening, and then we can regulate how we cause fruit aging and fruit ripening. Also, NMR is important when we have to do natural product extraction from plants and microorganisms. So this is a non-invasive way of having a complete plant extract and trying to find what all components are present in the in your mixture. Then definitely biologists are thrilled with NMR for the possibilities it is going to give you. You can do biopolymers, your DNA, RNA, all types of lipids can be studied by NMR. Lipids generally are studied more by your solid NMR, and your biopolymers, RNA, DNA, which are soluble, which can be easily solubilized and can create homogeneous solutions, are preferably studied by solution NMR. You can also study aggregates of proteins with NMR. So we can elucidate the 3D structure of your biomolecule, whichever is of interest to you, and we obviously know that we have protons present in it, we have carbon and nitrogen freely present in your biomolecules, and so hence there is no need for additional marking. We can study we can study the interactions over large distances. There are certain techniques such as NOE. We will discuss about them. We can do the solution structure under physiological conditions. This is one variation which we face, which is an advantage in a sense that you don't have to go to the process of first creating a crystal of a very purified protein. You can study the protein or any biomolecule in its near physiological condition, in a buffer, if you must say. The buffer may have all the components for its stability and its functionality. So when the buffer is there, you keep your protein in solution. You don't have to crystallize it. Definitely you have to maintain it at a concentration at which it does not precipitate or it does not have any deforming molecular interactions. So we can study solution structure under physiological conditions, and as we move ahead in this lecture, we will see the contributions of Kurt Woodrich, who received his Nobel Prize in 2002 for three-dimensional study of protein structure determination by NMR. Then we can study protein folding. Protein folding is again one grand challenge we face. Despite 1955 onwards, we studied Christian Amfinson's experiment where proteins were folding by itself because of their primary structure guiding the three-dimensional structure. But still we haven't advanced enough to understand how protein folding occurs. And because protein folding occurs in the solution, even if you imagine a cell, what is there? In a cell, it is an aqueous environment. All the ions are going to be present around a protein molecule and they will guide the protein to be formed. Not always the ions, but yes, the hydration around the protein will guide how the protein will fold. So these studies can be very much carried out by NMR, and its sensitivity is extremely good for these kind of studies. Then we can study molecular dynamics. Several enzymes, several immunoglobulins, several protein complexes show bindings and mobility within their structure. This mobility and binding is characteristic for their catalysis or for any function they have to perform. We can study all this by NMR. We can distinguish what are those domains which are showing mobility or which are causing the function. So we can demarcate it, we can study it even more in depth so that we know what are the properties of the enzyme which actually gives it its characteristic catalytic property. Then we can study interaction of molecules. How do enzymes interact with their substrate? Where do cofactors bind? What type of inhibitions may occur? Again, this can be extended to what we do in the last point, drug screening and design. It's an immense field of study where we have to determine what will be the drug which can be your cofactor or inhibitor, and how does it modulate the structure of an enzyme to give the desired outcome, either to inhibit the enzyme or to enhance its activity. And you know, enzymes are very much important for carrying out any biological process. So by intervention of molecules and compounds and drugs, we can modulate how these pathways proceed. Then we have kinetics of reactions. We will see how NMR can be used for studying kinetics, because NMR, when we do the radio frequency pulse onto the molecule of study, it takes up the energy and it processes, and we will see the phenomena. It relaxes back. This relaxation is very slow. If you are aware of absorption spectroscopy, where you are doing electronic phenomena, where you see electronic transitions, they are very fast. What has to be done in an electronic transition? You have an electron in its ground state, it goes to the excited state and it comes back. But when we are talking about nuclear phenomena, we are talking about spinning of a nucleus. So by the time a nucleus spins slowly, an electron would have taken up several transitions. So the nuclear phenomena is about 10 raised to power 9 times slower than the electronic transition phenomena. So these can be used for studying kinetics of reactions. Then we can determine the catalytic mechanisms. We can determine how the ionization changes. We can determine the chemical properties of the functional group, which functional groups are actually interacting when catalysis is occurring. So also you must be aware, or if you are not, we will take those things up. Proteins undergo this structure. When we are talking about protein folding, they undergo this structure formation not by very strong interactions, but these are small weak interaction. The 5 types of weak interactions, hydrogen bonding, electrostatics and hydrophobicity, which actually govern how the protein will come together into its folded conformation. So you can study even these kind of weak interactions, hydrogen bonding and hydration, and these two are the most important forces for any molecule to have its conformation, 3-dimensional conformation. We have discussed drug screening and design. We will take this up little later also. Another aspect which is based on the principle of nuclear magnetic resonance itself is in the imaging techniques. Earlier on, we were talking about analytical techniques where we were interested in the chemical structure, conformation and quantification. Here, we are more interested in looking at the gross phenomena which is occurring when we are doing imaging. Imaging is when you are trying to view something, maybe its surface or maybe its section. This is very important when we do clinical studies. You must have heard about MR, magnetic resonance scans. So MRIs. So imaging is one phenomena based on NMR. We also have NMR microscopy. Here signals vary with the nuclear density. So without cutting, without sectioning the organism or system, we can look at its internal structure and arrangement of nucleus in it and determine and form an image out of it. Also we can do in vivo NMR where we can, without cutting, look at the internal structures. NMR has been used to study metabolites like serum, urine. etc. And since 1960s, scientists have been using NMR to look at those metabolites which may not be produced in very large quantities to be detected by other analytical methods, but these could be markers for certain diseases. So scientists have used it to study how tumors and tumorigenic and non-tumorous tissues produce different NMR signals, and they can look at those minute peaks and tell if there is a possibility of tumor. Also, we have NMR tomography, and this technique is definitely advancing more and more, and definitely it will eliminate any need of doing a biopsy, because with this NMR tomography you can look at sections of the body, of the human body, and look at its nuclear density. Generally we look at the proton, and we can find by the dynamics of the proton in that location how is it different from a diseased or a healthy sample. So NMR tomography is there, combined with, if you can do a metabolite study, then you can have a complete picture of where is the disease starting. So I was saying that we can study geography with the help of NMR. So NMR also is important when we are doing environmental studies. We have to do a lot of monitoring, biomonitoring, we have to do monitoring for pollutants and several changes that occur. So generally we need soil samples, water samples for all types of metabolites or all types of compounds that may be present there. Sometimes we have to study degradation of certain compounds over time. How does it happen if you have any plastics in soil, and how do they degrade? If there are any pesticides, how do they degrade? So we can study these degradation studies and look at what are the what are the chemical changes that occur in the molecule over time using NMR. So 13C NMR is very much used for it. We can also quantitate how much is the pesticide present, how much it has degraded. We can use it for monitoring, and you'd be glad to know that we can do surface NMR. So you can see they are studying surface NMR in the North Pole, and they are doing studies for finding what is the geoelectric status of this place. That can tell you about water currents, that can tell you about aquifers and groundwaters. Again, you have the rifle bore hole NMR, where you bore the hole and you try and study the geoelectrical properties of that particular location and find the location of aquifers. Aquifers is those areas under the surface of earth which have water. So water is protons, and we can definitely study by these techniques. So when we've talked about this technique, now let's talk about its little origin. So where did we start from and where we have come? So this is the 1960s. Schulre had made this Varian, which was just a 40 megahertz system. It was in collaboration or being hosted very near to Stanford. They were able to develop this system, and now on the right you can see the latest 1 gigahertz NMR magnet, and this has a magnetic field of 23.5 Tesla. Generally what we have in our labs is around an 11 Tesla magnet. So these are definitely advancements going, and as and when advancements are occurring, we can say more and more high resolution structures can be obtained, and more understanding about the mechanisms and biophysics can be obtained with these. And definitely the spectrum of materials that can be used to study with NMR is enhancing. So look at how the scientists have been contributing to this field. We had Edward Purcell and Felix Bloch, who were in the year 1945. They were studying phenomena of NMR, and they were doing independent studies. One was in Stanford. Felix Bloch was in Stanford, and Felix Bloch also we will be studying about Bloch equations. Then we had Edward Purcell, who was at Harvard. Both independently discovered the phenomena of NMR signals. but they received a joint Nobel Prize in Physics. Then we have Herbert Gutowski, David McCall and Charles Schlichter at the University of Illinois, and they were studying how spin-spin coupling, a measure of atomic interaction within a molecule, occurs. Students, this is a very important aspect. We will be looking at how spin-spin coupling is an important aspect. So let's remember these people when we study that. And again, at the University of again, we talk about what is the basis of generation, or how does the phenomena of NMR came about. It is when we started thinking about quantum mechanics, I would say, when we started knowing that everything is quantized. When in 1920s, Niels Bohr suggested the quantum theory, we could talk about the absorption and emission phenomena of spectra of atoms, and these spectra always showed discrete lines, suggesting that there is nothing in between and there has to be some discrete quantization when we are talking about either energy levels within electrons, or there are some specific energy levels when we are talking about even the neutrons and protons. Then we had a very famous experiment in 1921 with Stern and Gerlach. This experiment has been extremely groundbreaking because it laid the foundation of how a silver atom beam was deflected by magnetic field. So you can see that there is a magnet, and this beam is coming of silver atoms, and there is a deflection from its original path. So this experiment formed the basis of understanding that nucleus has some particles which has a orientation or which has a magnetic component, and when this magnetic component interacts with an external magnetic field, it will show some sort of interaction or deflection. Then Unbeck and Goldsmith, they understood that an electron is also spinning, and this results in the angular momentum. So that is what a very important concept we come to with the magnetic dipole moment. When we talk about the neutron, it's spinning because it is a charged part of a proton. Because of it being a charged particle, its movement causes generation of electric current. Just like when you have your solenoid or any wire through which electric current is going to pass, a magnetic field is generated. So this kind of magnetic fields are also generated in these atoms, which are composed of protons and electrons. So this was first discovered by Unbeck. Then again we have Schrödinger and Heisenberg who discovered about uncertainty, and Schrödinger who discovered about particles and quantum theory he gave. So this was, you replaced old ideas and you took up new aspects of looking at particles, not as just particles but as waves. So the resonance property was also studied. So resonance is when two particles start to behave in a similar manner, or if they exchange characteristics or resonate with the same frequency. So they studied. Then Rabi observed nuclear magnetic resonance in his lab when he passed a beam of lithium chloride through a strong constant homogeneous magnetic field, and a small oscillating magnetic field was applied perpendicular to it. So this is where the critical aspect of Larmor frequency, this is where the origin of RF pulse is going to be. This is where we are going to talk about how do we disturb the alignment and then we cause the relaxation, and this forms the basis most partially. This is all that happens in a nuclear magnetic resonance experiment. So we are having, when the frequency of the oscillating field approaches the Larmor frequency of the nucleus in question, resonance occurs. The absorption of energy is recorded as a dip in the beam intensity as the magnetic current was increased. All these people were definitely rewarded for their contribution to development of NMR. 1943 Stern received his Nobel Prize, and then 1944 even Rabi was awarded with the Nobel Prize, and Purcell and Troy, they were also awarded with Nobel Prize in 1952. We will also talk about Overhauser, and we will be discussing Overhauser effect, in which if there is a small alteration in the electron spin of the population, it would produce a large change in the nuclear spin polarization. So, these effects are very important when we are going to study materials and when we are going to study long range interactions. Then there were people, even in 1957, Lottebier and Holm, they first recorded the C13 NMR spectra. And in 1961, Schulre introduced, he is the founder of the company which is into R&D of NMR spectroscopes, and he introduced the Varian 60, and we have seen the picture of it. And so let's pause at what we have learned till now. We have discussed about the history of NMR, and we have discussed about what are the applications of NMR. So students, we will talk about what are the aspects of NMR we have to study, what are the small little concepts we have to keep in mind, and then we will take them up and do all the mathematical calculations pertaining to them. So with NMR spectroscopy, it is a spectroscopy because you are going to use electromagnetic radiations in it also. Despite the nuclear and magnetic aspect, when we are using radio frequency, so you can see radio frequency will lie in the range of 10 raised to power 6 nanometers. This is again the region in which you work your radios, and in which most of the handheld radio sets work. So it is that region of electromagnetic spectrum, and hence this makes nuclear magnetic resonance a spectroscopic technique. So what is the N in the N, M and the R? The nuclear properties that we will look at are the nuclear spin, and because there is a spin, it generates a moment, angular moment, and this angular moment results in the nuclear magnetic moments. So we have to first choose or select a nuclei which will be showing nuclear spin. As we will go further, we will find that nuclear spin is not inherently present in all types of atoms. So there are few of them, and why is that? So we will look into that. Then magnetic aspect comes from, of course, then there is a magnetic moment in the nucleus itself, and then we have a external magnetic field. So we have a nucleus which is itself spinning, or which is itself having an angular momentum. When this is placed in an external magnetic field, it will show certain phenomena. First one is the precision, that will result into the Larmor precision, and it will be characterized by the Larmor frequency. Then we have the nuclear Zeeman effect. This is the effect that talks about how quantization may occur. This is not a very clear quantization, but then this is splitting of the energy levels. Then we will have Boltzmann distribution. When a nucleus, a spinning nuclei, a micromagnet is placed in an external magnetic field, it will orient either with or against, parallel or anti-parallel to the external magnetic field. So this distribution is also governed by the Boltzmann distribution, and we will look at this equation. So the number of nuclei in the higher energy or lower energy state will be governed by this equation. And then where does the resonance comes from? And that is very important. Once you have placed the nuclei into the magnetic field, the nuclei have oriented with the magnetic field, then we can disturb this setup and cause flipping of the nuclei from one energy level to the other. And this flipping is caused by an external magnetic component, and as you know that electromagnetic waves do have a magnetic component. So if we apply an electromagnetic wave, the RF, it can cause this disruption, and once this disruption is caused, there is resonance that is generated from the nuclei in the lower to the higher energy state. So number of spin state that can occur, and or the number of possible levels that can occur, which will be a part of how we will study Zeeman's effect, is given by 2I plus 1. So what are the spin properties of the nucleus for NMR? When I said we need to have a selected nuclei for studying NMR property, we have to see that it has a spin of I equal to plus minus half. What does I equal to plus minus half means? This is the quantum number which we are talking about, the nuclear angular momentum quantum number I, and it should always be an integral or half integral or 0, but for it to be for NMR active, it has to be a half integral. So a nuclei having spin number I can absorb or emit electromagnetic radiations. So the magnetic quantum number M will have values of minus I plus 1 and plus I. That is, if we have I equal to 3 by 2, then M1 will be minus 3 by 2, M2 will be minus 1 by 2, 1 by 2 and 3 by 2. So a very quick checklist of how we can be selective about the nuclei that we are studying. We know that a nucleus or an atom is composed of three components basically: the neutrons, protons which are in the nucleus, and you have the electrons which are residing in the orbitals around the nucleus. So we have to see what is the number of neutrons and protons present in the atom of your choice. If you have a nuclei with even mass number and even charge, I will be 0. For example, we have carbon 12, and if we look at carbon 12, it has even mass number and even charge, it will not be NMR active, but its isotope carbon 13 will be NMR active. Likewise for oxygen and sulfur. So if a nucleus has even mass but odd charge Z, then if it is giving an integer I value, it will be NMR active. So when we have hydrogen 2, this may have both cases, and I will discuss with you that it may have an integer as well as 0 spin. If there is, and in that case it will become NMR detectable. So nitrogen, which is abundant, nitrogen 14, and then you have boron 10, all will be NMR active or detectable using this spectroscopy technique. Then we have nucleus with odd mass and I is equal to n by 2, where n is the odd integer. In case of hydrogen 1, carbon 13, nitrogen 15, phosphorus 31, fluorine 19. So these will have NMR detectable nuclei. That is to say that they have some spin. It's a very easy way to say how many unpaired protons, unpaired neutrons. Why are we interested in the unpaired protons and unpaired neutrons? When we have two protons, the two protons will lie, one of them will be in antiparallel sense and other will be in parallel sense, and hence they will cancel out the spin of each other, which will result in a 0 spin. So when the spin is equal to 0, it is not going to be useful for NMR studies. But if you have unpaired proton, it is giving you one spin of half. If you have, in the case of hydrogen 2, you have one unpaired proton and one unpaired neutron. So depending on the sense of the spin of neutron and the spin of proton, if both are parallel, then they will give rise to a net spin of half plus half, which is 1. But if one is parallel and one is anti-parallel, that is to say the proton is anti-parallel and neutron is parallel, it will be 0 and it will give rise to no net spin. Likewise, you can do calculations for all of the following. So this is the diagram which is showing you what I mean by the neutron and protons, if they are odd or if they are even, what happens. So this is what happens in case of atoms having even number of protons and even number of neutrons. So even numbers will tend to cancel the spin of either of the two. So for example, helium-4 has 2 protons and 2 neutrons, and 2 protons are paired in the same orbitals. So these are paired in the same orbitals with their magnetic moments, and these magnetic moments will oppose and hence cancel each other. Same is true for the neutrons that are present in the helium, which are again paired in their orbitals, and hence there is no net spin. Similarly, we can study for the C13 and C12 why there is a difference. But if you look at the helium isotopes which do not have even number of neutron, which have 2 protons and only 1 neutron, this kind of helium-3 will be NMR active. So we could tabulate what all nuclei which are available for us to study. We can also look at the abundance. We can say that proton 1 is abundance about 99.98%, which suggests that if you are looking at the environment or if you are looking at abundance of this nuclei in the chemicals and in everything, it is 99.98%. You will find your hydrogen 1 and the rest will be H2 or H3. Then similarly, if we are looking at carbon 13, its natural abundance is only 1.18%. So does it tell you something? If we have 1 bowl of sugar, only 1.108% of it, of the 100 grams, only 1.108 will be NMR active. So what you have in a field of space of lot many carbon nuclei, which most of them will be carbon 12 and only 1.1% will be C13. So even if you have a bulk of system, only few of them will be amendable to studied by NMR. Likewise, you can look at the abundance of N14. N14 is 99% abundant and N15 is only 0.3% abundant. Despite saying that both of them are NMR active, but N14 is slightly less sensitive and we use it less, while N15 is being regularly used despite its less abundance. So we do enrichment studies so that we can study N15 when we are doing biomolecules. Likewise, for other examples, you can see phosphorus 31 is 100% abundant. That is to say that all the phosphorus present in all the DNA will be NMR active, and hence it is a ready sample for studying with NMR. So looking at these abundance, there are other factors also which make it more amendable or less amendable for studies, and those are the spins and their gyromagnetic ratios, and we will talk about those. So as I was saying, what can the abundance and gyromagnetic ratio tell us about how amendable is the nucleus for NMR studies? We can calculate the sensitivity of a nuclei when we are studying NMR. So the sensitivity will be proportional to the gamma, which is the gyromagnetic ratio, and then we have abundance. So if you are to choose between, will you want to study proton or do you want to study C13, you can see that if I do a ratio of the two, I find that the ratio of sensitivity is 63, and here I can say that proton is 5,000 times more sensitive than C13 NMR. Both of them give very different information. Both of them have their advantages and disadvantages, and we will discuss in the coming lectures about their specific utilities. So another thing is, do all nuclei feel the same magnetic energy? Now we know that they have a spin, but do they feel the same magnetic field? We know that the Earth's magnetic field is only 30 to 60 microtesla compared to, as I was talking about, the NMR instrument where we had 23 Tesla. So when we have MRI instrument, we have even 1.5, 1.3 or Tesla. So NMR, when we have in our labs, we start from 4.7, which is a normal 300 megahertz magnet, to 23 Tesla. So if we were to keep all these nuclei under different magnetic field strengths, what will be the effect on the nuclei? So we will look at those. So there is a very simple formula if you want to see the conversion. If suppose you are studying one nuclei in a 4.7 Tesla magnet and the other nuclei in 11.5 Tesla magnet, then how will you find the conversion? What is the magnetic field assessed by the nuclei? And that can be easily given by F is equal to gyromagnetic ratio into the magnetic field. So you can easily do this calculation. So when I am saying you are keeping one nuclei in one field and then you are enhancing the field, what all changes are going to occur? I was talking about splitting of the energy levels, and here you can see if delta E is the energy difference between the two spin states and H is the Planck's constant and BE is the small magnetic field generated by the moment of the atom itself due to the electrons, and BO is the external magnetic field, which is definitely your very high high field strength magnetic field. So we can see that as we increase the magnetic field strength, the separation between the two spin states, these are the two spin states, is increasing. So this is where you can have a 30 megahertz radio frequency can cause the resonance. Here you have H into 300 megahertz causing the same flipping or resonance. So again, that was for the same nuclei under two different fields. But if we are trying to see all different nuclei, can we use the same probes or same frequencies of RF and same magnetic field? No, that is not so. We have separate RF and magnetic field for different nuclei. So if you want to study C13, then the RF will be around 30. If we are RF, we discussed RF being that pulse which causes the disruption in the spin states. So we have these. So when we study different nuclei, then we have to tune each probe for these specific nuclei. So this is what nuclear magnet moment we were talking about. If nuclei are like, look at the spinning proton here and how it is similar to a bar magnet. So when we have a proton which is positively charged surrounded by electrons, we will look at those magnetic moments separately. That is another magnet which that is another magnetic field generated because of electron. Here we are talking about the spinning of the proton, and this generates a magnetic moment as seen by the circular arrow. So this is the direction of the angular momentum, and this is the direction of the field that is generated. This is the vector of the field that is generated, which is B, and you can see the lines of magnet such as if it was the north pole from which the magnetic lines were starting and ending on to the south pole. Similar to what you see in a small bar magnet, you have a north pole out of which is emanating the magnetic field lines. Point of difference here is that your bar magnet is static. It is not showing any momentum, it is not showing any rotation over any axis. So the way it is going to be in an external field, will be slightly different as compared to a spinning neutron, compared to a spinning proton. Whenever we keep one nuclei in an external magnetic field, this is not how the orientation will be, not very parallel to the external magnetic field, and we will look into those things. So this is clearly telling you what all the possible things can happen when you keep a small magnet, a small bar magnet in an external magnetic field. So you have a small magnet, if it is kept in a horizontal, then it will try and align such that the opposite poles are facing each other. If you are aligning the north to north pole, then it is going to be a less stable condition, but if you are aligning the north to south, it will be an attraction and it will be a more stable conformation. So the stability is arising in this complete system. It is not that these two options cannot occur. The more stable and less stable orientations will occur, but one will be more stable and one will be less stable. So when we see this again for the nuclei or the proton, if the proton is present within the external magnetic field and oriented horizontally, it will also try to align to bring its north pole opposite to the south pole of the external field, and likewise you have a more stable when it is anti-parallel to the external field, it is more stable, and if it is parallel to the external field, it is more stable, and if it is anti-parallel to the external field, it is less stable. But again a caution, these two states, both of them can exist. It is not that if you keep a nuclei, if you have all these nuclei, so on your left you have a field where there is no magnetic field, it is zero magnetic field. So all the nuclei are present in their orientation, they are spinning about their axis, but they are not facing. So this is only Earth's magnetic field if there would be. So the 60 microtesla is only present. It's not zero magnetic but very less magnetic field. It is not sufficient to align them or orient them parallel or anti-parallel to it. But now if I apply a magnetic field, and you can see there is splitting occurring. This splitting can be in two states if we have I equal to 1 by 2, but if I have more, if I have 3 by 2, what will be the case of splitting? So you can have even more number of energy states, and hence the nuclei will tend to orient themselves under those states. So you have these nuclei, once they are under external magnetic field, they are orienting as previously shown, the beta state, which is the less stable state, more energy, and then you have alpha state, which is the lower energy, higher state, higher stable state, and there is an energy gap. This energy, this is very small energy gap, which is the delta E, and it is proportional to the gyromagnetic ratio and the applied magnetic field. So if I am saying that this energy gap is proportional to the magnetic field, that means if I vary the magnetic field, this gap can be varied. Likewise here, very low magnetic field, there was no gap. So what can happen to this gap? So two things we are learning from this slide, that there can be splitting. The splitting can be not just in two levels, the splitting can be in more than two levels. So if there are I equal to greater than half, then there are multiple transitions, which of course right now you will not be required to know, because we are focusing on proton, which is having only spin half, and hence we are having only two energy levels. So in the next question is again, why, if one is stable and one is less stable, why should not all the nuclei be present only in the alpha state, where there are parallelly aligned to the external magnetic field? It is not so, because again here we will talk about the Boltzmann distribution. So when we see all these spinning nuclei are present at room temperature, they are governed by the Boltzmann distribution equation to how many will go to the beta state and how many will go to the alpha state. And this calculation, if we do, we find that there is extra energy that you need to supply to cause this conversion of all the beta to the alpha, and this does not gives you any benefit. So it is better that they remain in those two separate states rather than orient only in one spin state. So if we were to look at the equation, we have delta E is equal to 2.65 into 10 to the power minus 25 joules, while the K, which is the Boltzmann constant, and T, it is only 4.14. So when we take a ratio of these, it is still 6.4 into 10 to the power minus 5. What is it telling us? It is telling us that the delta E cannot be superseded by the temperature or room temperature when we are working on it. So hence the energy gap will remain. So what is the Boltzmann distribution telling us? When there is net absorption of radiation to occur, the low energy state is more populated, and if no net absorption is possible, then it is saturated. This we will come to when we are talking about relaxation and RF. So Boltzmann distribution is a very small formula which tells you how many nuclei are going to be in the upper or the beta state and how many nuclei are going to align in the lower state. So if you are starting with a 2 million nuclei, 1 million will go to the upper state and 1 million will go to the lower state, and this is governed by this very simple equation, e raised to power minus delta E divided by Boltzmann constant into temperature. So the difference in population of these two states is very minute, but this very minute difference is the sole basis of how NMR phenomena is going to occur. NMR is sensitive only because of this very small number of nuclei being more or less in the alpha and the beta state, and this difference in number of nuclei is sufficient to cause or generate a very small amount of voltage, which we will be able to capture in the FID. So, so this is how we relate delta E to the magnetic strength. So if we know delta E, we know that gyromagnetic ratio, and we can correlate it to the B naught. So you might face numericals in which you can use this simple formula. So this is what it actually looks like when I am saying there are 2 million nuclei present when there is no magnetic field, and when we apply a small magnetic field, it splits. See the energy gap. See only there is a difference of 16 nuclei. Now if I increase the magnetic field, even there is more energy gap and there are more number of nuclei in the alpha, or maybe there is a larger difference in number of nuclei, and here we still have 128 out of only 1 million which are different here, and this is sufficient to generate a small voltage, and this energy gap is what is responsible or which will be modulated with the RF. So with these we have understood about Boltzmann distribution, we understood about Zeeman effect, which is splitting of the nuclear spin into two. So after using these two, we will talk about in the next coming up lectures about what happens when we have nucleus in the magnetic field, and I will introduce the concept of nuclear precision.
With this note, thank you ma'am, thank you so very much for giving us a productive session, and I want to request friends that if you have any queries or if you want to give your feedback regarding this particular lecture, then you can mail us at info.cc@nic.in. Surely we would love to solve your queries the next time when Dr. Nateen visits our studio. We would be taking your queries. Till then, take care, goodbye, and yes, very soon we would be coming again and would be discussing more as Dr. Gulati said. Thank you ma'am, thank you so very much.
Thank you, Kritika. Thank you, students.